Gold is one of the most desired materials on Earth. Entire civilizations search for it. Wars were fought over it. Fortunes were built on it. Yet even today, most people still don't understand how it truly works. Because gold rarely appears the way people expect. It hides inside broken stone, moves silently through rivers, follows invisible geological patterns, and concentrates in places most people walk right past. The Earth leaves clues in landscapes, in river behavior, in pressure zones, in the ugliest rocks imaginable. But unless you understand those clues, gold remains invisible. Cut to crushing rock, reveal gold. In this documentary, we uncover the complete hidden journey of gold, how it forms, how nature extracts it, how rivers move it, why most people never find it, and how gemstones and gold are connected deep beneath the earth. This is not luck. This is geology. Gold has always been seen as the ultimate symbol of wealth, power, and endurance. For centuries, men have gone to impossible lengths to extract it, from diving deep into mountain tunnels, to washing entire rivers with heavy pans, to melting stone with complex chemicals. Yet what if I told you that long before modern tools, long before mercury, cyanide, and machines, nature itself had already written the script? Hidden in the folds of rock and soil, written by wind, water, heat, and pressure, lies a method, an ancient forgotten way to extract real gold without a single tool in hand. And if you listen closely to the earth, you can still use it today. The first clue comes from water. Flowing rivers, even without pans or sieves, act as natural refiners. For millions of years, water has been the tool that never sleeps. It moves relentlessly, carrying sand and stones and separating light from heavy. In the quiet bends of a stream, gold collects where water slows, settling beneath layers of sand. Without lifting a hand, you can already find gold simply by watching where nature drops it. It lies hidden beneath black sands, deep in the crevices of rocks, and even along the edges of gravel bars. This isn't chance. It's gravity at work, constantly sorting materials without any human tool. The secret is knowing where to look. And once you see the shimmer, you realize that nature has been panning gold for you all along. Yet water alone is only half the method. The other great tool is fire. Imagine lightning striking a dry hillside, a wildfire raging through forests, or even the heat of the sun baking the land until it cracks. Heat changes rock. It fractures veins, makes stone brittle, and opens pathways that once sealed gold inside. Over centuries, cycles of heat and cold, expansion and contraction, break apart host rock, freeing the gold little by little. When rain arrives, it washes those freed particles downhill, feeding streams, filling valleys, and leaving golden traces scattered in the soil. The mountain does the mining, the storm does the crushing, and the river completes the refining. All of it without human hands. If you've ever walked through an eroded canyon, you've seen the evidence. Boulders split open by heat, quartz veins exposed like scars on the surface, and patches of soil rich with minerals that look darker, heavier, almost magnetic. These are natural furnaces at work, creating channels through which gold escapes its prison. You don't need a pickaxe. You don't need explosives. The earth has already done the work, slowly, patiently, in ways more precise than any machine could replicate. But even more fascinating is how wind and time contribute. Dust storms sweep across dry lands, lifting lighter sands into the sky while leaving behind heavier particles that refuse to move. Among those survivors is gold. Over hundreds of years, winds strip landscapes bare, erasing the cover and leaving behind golden crumbs that gleam under the sun. In deserts where rivers no longer flow, wind becomes the new river, separating the worthless from the valuable. To the untrained eye, the ground may look barren, but those who know the secret understand. Where the soil is scoured and the lighter grains are gone, the stubborn glitter of gold often remains. Another part of nature's method lies in black sands, the quiet clue prospectors often overlook. Without a pan, you can still see them. Black sands are iron-rich, heavier than ordinary grains, and they act as natural companions to gold. Wherever these sands collect, there is a chance that tiny flecks of gold lie hidden among them. In fact, some of the world's richest deposits were first hinted at by nothing more than dark sandbars glistening in the sun. The trick requires no equipment, just eyes trained to recognize the subtle signs left by the earth. And once you spot them, you realize you've stepped into a natural concentration zone, a place where gravity, water, and density have already done the refining. Of course, the story doesn't end there. Imagine a hillside scarred by landslides. As rocks tumble, the lighter materials scatter far and wide, while heavier elements, like gold, remain lodged in cracks, trapped in soil pockets, or exposed in newly broken veins. The landslide itself becomes nature's mining event, revealing treasures that may have been hidden for thousands of years. When you walk across such terrain after heavy rain or shifting earth, you might see tiny flashes in the dirt, evidence of nature's own excavation. Without shovels, without drills, the mountain itself tears open and delivers the gold. Nature also uses freezing and thawing as silent tools. In colder regions, water seeps into cracks of quartz and other host rocks, freezes in winter and expands. That expansion pries the rock apart, fragment by fragment. With each cycle, the gold within is freed, ready to be carried away when spring melts arrive. Over centuries, this cycle repeats, breaking down entire veins and scattering golden fragments across valleys. It is a slow but unstoppable process, and the result is a natural distribution of gold that continues even now. To see it, you need only trace the trails of broken quartz scattered across hillsides, following them like breadcrumbs to where nature has already released her hidden wealth. But perhaps the most astonishing method of all is the role of soil and clay. Many think of gold as always being shiny and visible, but often it hides within fine clays that grip it tightly. Rainwater and erosion slowly wash away the clay, releasing gold into the open. In some cases, entire deposits of alluvial gold were uncovered not by miners, but by seasonal floods that stripped away layers of soil, leaving rich golden streaks behind. Farmers plowing fields, shepherds walking pastures, travelers crossing dry plains. Many stumbled upon gold simply because nature had exposed it beneath their feet. The earth itself had done the mining, waiting only for a watchful eye to claim it. To fully grasp the scale of this natural refining, think about how long it takes. Thousands of years of rain, fire, frost, wind, and erosion combined to do what a modern prospector might try to replicate in a single season. But the difference is clear. Nature wastes nothing. It sorts, concentrates, and delivers gold in ways that require no chemicals, no machines, and no tools. All it asks is that you pay attention. The bend of a river, the darkness of sand, the fracture of a hillside, the sparkle after rain. These are signs as old as time, hints left by the planet itself. The beauty of this forgotten method is that it shows us gold, not as something forced out of the earth by violence, but as something revealed by patience. The mountains collapse, the rivers carve, the winds strip, and the elements refine. And in the end, gold, the most stubborn, enduring of metals, remains. All you need to do is be there when the earth has finished her work. This is why even today, experienced prospectors will walk landscapes without carrying heavy tools. They read the language of the land. They see how quartz veins align, how black sands pool, how river bends create traps. They watch the color of soil change, notice where vegetation struggles to grow, and mark the scars of landslides. With no pan, no pickaxe, no sluice, they can still locate gold because they understand nature's process. The earth itself is the greatest prospector, and all we must do is follow its signs. When you step into the field with this knowledge, you are no longer blindly searching. You are walking in partnership with forces that have been at work for millennia. The mountain is your miner. The river is your refiner. The wind is your separator. The frost is your crusher, the soil is your filter. Together, they form the greatest gold extraction method ever known, one that requires nothing but awareness. So the next time you wander through a canyon, climb a hillside, or cross a dry desert plain, remember this: gold doesn't always need to be extracted with tools. Sometimes the most powerful methods are those written by nature itself. And if you pay attention, if you look where the signs point, you may find yourself holding in your hand a piece of the Earth's most enduring treasure. Real gold, brought to you not by machines, but by the secret hand of nature. And as we close today's journey, remember that the Earth is always whispering her secrets to those who listen closely. Gold has never truly been hidden. It has only been waiting for the right eyes to see it. Here at EGS, we don't just chase treasure. We uncover the forgotten truths of how nature herself reveals it. If you felt the thrill of discovery in this story, imagine what's still waiting just beneath your feet. Stay curious, stay relentless, and let the land guide you to its hidden wealth. This is KD Gems, where every stone turned and every secret told brings us closer to the gold that endures forever. Most gold found in rivers is not there by accident. It is there because physics, geology, and time placed it there in predictable ways. Long before a prospector ever walked into the area, the shape of the land, the type of bedrock, and the behavior of flowing water had already decided whether gold would concentrate at that location or pass straight through. This is why experienced field geologists and serious prospectors do not begin by panning. They begin by reading the river itself. In North America, especially across the western United States, Alaska, and parts of the Appalachian region, placer gold deposits follow repeatable patterns tied to erosion of hard rock sources upstream. When gold erodes out of quartz veins or mineralized zones, it enters the drainage system. From that point forward, it behaves very differently from sand, gravel, or lighter minerals. Gold is dense, about 19 times heavier than water, and that density controls everything about where it stops moving. To understand why a river bend matters, you must first understand how moving water sorts material. When water flows in a straight channel, velocity is relatively uniform, but rivers rarely remain straight for long. As soon as a curve begins to form, centrifugal force pushes faster water toward the outside of the bend. That outer bank becomes a zone of erosion. You often see steep cut banks there, sometimes exposing roots, compact clay, or even bedrock. That is where the river is actively removing material, not depositing it. The inside of the bend is the opposite environment. Velocity drops, turbulence decreases, the river loses carrying power, and when water loses energy, it drops the heaviest material first. This is the first rule. Gold settles where energy decreases suddenly. On the inside of a bend, you will typically see a point bar, a gently sloping accumulation of gravel, sand, and cobbles. To an untrained eye, it looks ordinary, but to someone evaluating placer potential, that bar represents a natural sorting machine that may have been operating for thousands of years. Gold moving downstream does not travel evenly across the channel. It moves during high-energy flood events, bouncing and rolling along the bottom in a process called traction transport. Unlike lighter sediments that remain suspended, gold rarely travels far without making repeated contact with the bed. Every time flow velocity drops, even slightly, the gold attempts to settle. Now consider what happens during seasonal flooding, which is the dominant transport mechanism across much of the United States. During a flood, rivers gain the energy required to mobilize large gravel and cobbles. Gold that has been sitting in upstream cracks or benches can be re-entrained and pushed downstream. But as the flood begins to subside, velocity decreases unevenly throughout the channel. The first places to experience that drop are zones of expansion, inside bends, downstream of obstructions, and where the channel widens. These become natural gold traps. The key point is that rivers do not distribute gold randomly across a bar. They concentrate it along very specific microenvironments that repeat from one drainage to another. This is why two prospectors can work the same bend and have completely different results depending on whether they understand where to test. In field evaluation, the first thing to examine is not the gravel surface. It is the relationship between the bar and the bedrock beneath it. Gold, because of its density, will continue migrating downward through loose material until it either reaches bedrock or encounters a compact layer such as clay, caliche, or tightly packed gravels known as hardpan. This lower boundary is called the pay layer. Across many American placer districts, studies have shown that the richest concentrations occur within the lowest few inches above bedrock. This is why shovel testing, without understanding depth relationships, often leads to the false conclusion that an area is barren. At a productive bend, the geometry of the channel directs heavy material toward predictable lines called pay streaks. These are not always visible from the surface. They form along paths where the river's heaviest flow once traveled before slowing. Black sand concentrations after runoff events. Black sands, primarily magnetite and other heavy minerals, are important indicators because they behave hydraulically similar to gold. Where you see consistent accumulations of black sand trapped behind cobbles or inside shallow depressions, you are looking at zones where the river has already demonstrated its ability to retain dense material. However, black sand alone is not proof of gold. It is evidence of the right physical environment. The second major control on gold concentration at bends is bedrock topography. Bedrock is rarely flat. It contains fractures, joints, weathered pockets, and irregular undulations. These features act like riffles in a sluice box. During high flow, gold is driven into these depressions and can remain there long after lighter material has been flushed away. In many productive U.S. placer streams, the most valuable ground has little to do with the modern bar and everything to do with ancient channel positions preserved in bedrock lows. Modern rivers often inherit gold from earlier landscapes. During glacial and post-glacial periods, drainage systems shifted repeatedly. Channels migrated laterally, abandoned segments, and recut new paths. Gold that was concentrated in an ancestral channel can be partially remobilized and reconcentrated where the modern river intersects that older deposit. When evaluating a bend, it is therefore essential to look beyond the active waterline. Elevated benches, terraces, and older gravel remnants along the inside curve may represent former channel positions. These paleochannel features can host richer concentrations than the modern stream itself because they experience prolonged periods of stability during which gold could accumulate undisturbed. In the United States, many historically productive placer districts exploited exactly these elevated deposits once miners recognized the pattern. Another factor influencing whether a bend holds gold is upstream geology. A perfect hydraulic trap is meaningless if the drainage does not intersect a mineralized source. Gold in rivers originates from lode deposits, typically quartz veins or disseminated mineral zones formed during hydrothermal events. Over time, weathering breaks down those host rocks, releasing free gold particles that enter the watershed. If the drainage above a bend does not cross favorable lithologies, no amount of hydraulic sorting will create a deposit. This is why serious evaluation always combines geomorphology with regional geologic mapping. Indicators of favorable upstream sources include quartz vein, floating gravels, iron-stained or oxidized rock fragments, altered volcanic or metamorphic material, sulfide mineral remnants such as pyrite cubes, angular quartz pieces suggesting limited transport distance. When these materials appear within bar gravels, they suggest erosion from nearby mineralized bedrock rather than transport from far upstream. Shorter transport distances often correlate with coarser gold because larger particles have not yet been ground down by extended movement. Particle size matters. Coarse gold settles more rapidly and forms tighter concentrations near source areas. Fine gold can travel farther and requires more careful sampling strategies because it distributes over broader zones. Inside bends that lie relatively close to known hard rock mineralization, therefore tend to produce more consistent placer values than bends located many miles downstream. Most people fail at gold panning because they look in the wrong material. This ugly rock is one of the strongest indicators of placer gold. Value in geology rarely announces itself. It forms slowly, concentrates quietly, and reveals itself only where natural forces repeat the same actions over immense spans of time. Most people believe gold panning is about luck, about randomly scooping sediment and hoping something flashes back. But experienced prospectors know better. Gold does not move randomly, and it does not stop randomly. Gold is one of the densest naturally occurring metals found at Earth's surface. Because of that density, gold behaves very differently from sand, gravel, and lighter minerals once it enters a river system. When gold is released from its original host rock, often quartz veins or mineralized bedrock, it does not travel far unless water energy is extremely high. Even then, gold moves in short, controlled steps, settling repeatedly wherever water velocity drops. This is why gold panning success is never random. Every productive pan reflects a specific reduction in water energy combined with a stable trapping surface. One of the most reliable gold panning spots exists where water slows naturally, but not completely. Inside river bends, behind large rocks, at the downstream edge of gravel bars, and along shallow inside curves, water loses just enough energy to drop heavy materials. Gold settles first, long before black sand or lighter concentrates. These areas may look unremarkable, but geologically they function as natural gold traps. Over time, season after season, flood after flood, gold accumulates there layer by layer, often just inches below the surface. Another overlooked panning zone is where rivers transition in slope. When a river moves from steep to shallow terrain, its carrying power drops suddenly. This is where gold that traveled during high-energy events finally settles. These transition zones often sit far from dramatic scenery. No waterfalls, no exposed bedrock, just calm-looking sediment. Yet these quiet zones can hold gold concentrations far richer than fast-moving water upstream. Gold also responds to microfeatures most people never consider. Small depressions in compacted gravel, shallow cracks in clay layers, and subtle changes in sediment color often mark places where gold pauses during transport. Clay is especially important. While clay itself does not contain gold, it acts as a sealing layer, preventing gold from sinking deeper and allowing it to accumulate directly above. When panning sediment just above clay, results are often significantly better. This is why experienced prospectors do not pan randomly. They read the river the same way a geologist reads rock formations, by observing flow patterns, sediment sorting, and material layering. A productive gold pan is simply confirmation that the underlying geology and hydraulics are working exactly as expected. It's also important to understand why simple gold panning locations continue to replenish. Gold is constantly being released upstream through natural erosion. Every storm, freeze-thaw cycle, and seasonal flood introduces new material into the system. Rivers act like long-term processing machines, sorting, concentrating, and redepositing gold repeatedly. That's why the same simple panning spot can produce gold year after year, even after repeated activity. This is also why crushing tools, chemicals, or heavy equipment are not required for this process. Gold panning works because nature has already done the separation. Water, gravity, and time have removed everything unnecessary, leaving behind only the heaviest, most stable materials. From a geological and financial perspective, this is what makes gold panning so powerful. It demonstrates how value concentrates naturally without human intervention. The same principles that govern placer gold formation also govern larger mineral systems, only on different scales. Understanding this process builds real geological intuition, not speculation. Gold panning is not about chasing glitter. It's about recognizing where Earth repeatedly places value and why it does so with such consistency. That is the difference between guessing and understanding. Most people believe gold discovery requires heavy machinery, chemicals, or advanced mining equipment. In reality, some of the most reliable gold indicators are visible long before any tools are ever used. Gold leaves behind unmistakable geological signals, and when you understand how to read them, the ground itself tells the story. This documentary explores how a simple, no-tool observation method can expose a hidden gold pocket by understanding how gold forms, migrates, and concentrates naturally inside host rocks over millions of years. Nothing here relies on guesswork. Everything is grounded in real geological processes that professional prospectors, mining geologists, and field experts have relied on for generations. Gold does not form randomly. It is transported by mineral-rich fluids deep underground, moving through fractures, faults, and zones of weakness in the Earth's crust. As pressure and temperature change, those fluids deposit gold into specific rock structures, locking it inside veins, fractures, and dense host formations. Over time, erosion removes softer surrounding material, leaving behind subtle but powerful surface clues. The first signal often appears as an unusual weight difference. Certain rocks feel heavier than they should for their size. This is not coincidence. Gold is one of the densest natural metals on Earth, and even when finely dispersed, it influences the overall mass of its host rock. Experienced eyes notice this immediately, while most people overlook it entirely. Texture is another critical indicator. Gold-bearing rocks frequently show internal stress patterns, mineralized fractures, and hardened surfaces caused by repeated fluid movement. These textures are not decorative features. They are records of geological activity. Smooth, featureless stones rarely host gold, while fractured, irregular, or quartz-influenced rocks often tell a different story. Quartz plays a central role in natural gold formation. When hydrothermal fluids cool, quartz crystallizes first, creating pathways where gold becomes trapped. These quartz veins can appear dull, stained, or even broken on the surface. Yet internally, they may contain fine gold threads invisible until the rock is examined closely or fractured naturally. The no-tool method relies on recognizing how gold influences the behavior of the rock itself. Subtle changes in color, density, fracture direction, and mineral association act like natural warning signs. These signs become stronger when multiple indicators appear together, rather than individually. Another overlooked signal is how a rock breaks. Gold-bearing stones often fracture along mineralized plains, exposing metallic glints, reflective surfaces, or darker mineral inclusions. These breaks are not random. They follow the same pathways once used by gold-rich fluids millions of years ago. Surface staining also matters. Iron oxides, dark mineral crusts, and reddish or brownish discoloration frequently appear where gold systems once operated. While iron alone does not mean gold, the presence of iron staining combined with quartz, density, and fracture patterns significantly raises the probability of gold nearby. One of the most powerful aspects of this no-tool method is pattern recognition. Gold rarely appears alone. It forms as part of a system. When similar rock types repeat across a small area, showing the same weight, texture, and mineral traits, it suggests a localized gold pocket rather than a scattered trace. Gold pockets form where geological conditions briefly align perfectly. Pressure dropped, fluid slowed, and gold had time to concentrate rather than disperse. These pockets are often compact, easy to miss, and extremely valuable when identified correctly. The mistake most people make is assuming valuable rocks must look impressive. In reality, gold-bearing stones often appear ordinary, weathered, or even unattractive. Their value lies not in appearance, but in structure, density, and mineral history.